Hi, in this video we're going to continue our discussion of lines, specifically section 12.5. Last video we talked about the basics. Make sure you watch that one first. Here we go. So, like I said in the last video, this is going to be a lot of examples. We're going to talk about lots of stuff that can happen. I have two airplanes plural, one. Airplane 1 is going to follow line 1, which has x equals 1 minus 2t, y equals negative 1 minus 3t, and z equals negative 2 plus t. And airplane 2 is going to follow path L2, line 2. And we're going to have negative 3 plus t. Sometimes we'll use a different parameter. Like if the first one was using t, this one might use s to make things a little more clear. I'm just going to try to show you how to handle it if it's not given to you like that. Y equals negative 2 plus 2t, and z equals 3 minus t. So again, like I was saying, would this problem be any different if they called these s's? No. Okay. Would the problem be any different if they called them T1 or T2 here? No. We have two different paths of these planes. And what they'll ask you is, are the paths parallel, intersecting, or skew? Now, skew is a new word, probably for a lot of you. In 2D land, there is only ever parallel lines and intersecting lines. Because there's so much more room, quote unquote, because there's a whole nother dimension, it's possible two lines might not be parallel and might not intersect. I'm going to draw such an example now. Feel free to think about it. There's ways to hold your arms where they're not ever going to cross, but yet they'll never actually be parallel either. So here's our XYZ. Say I have a line going way up here, and it's sort of running mostly in the y direction, but it's floating up there. And then I have another line down here that's perfectly parallel to the x-axis. It's actually in the xy plane. It might look like they're intersecting, but they're at different heights. Remember, if you're seeing this picture correctly, and I think it kind of looks like it to me, that one guy is way up there in a whole different plane than my guy in red at the bottom. That would be a skew situation. They're not parallel, you can see that. But nor are they intersecting. They will never intersect. They will never be parallel. That's what we mean by skew. You can see a GeoGebra example if you want. Okay. I also want to clarify the word, so skew is just the other option. It's non-parallel, but not intersecting. I also want to clarify an important thing. Sometimes the problems will ask you about collisions, and some problems will ask you about intersections. So lines can intersect without colliding. Collision means same point at the same time. Okay, right? We don't collide. I can go through the intersection of the road and you can go through the intersection, without us hitting our cars, right? I just have to go through a little bit later than you. But our paths will intersect. Okay? That's all we mean. Be careful with the language. All right, so starting from a blank slate, so to speak, we're going to check three things. We need to check all three of them. We're first going to see if the lines are parallel. Then, if they're not parallel, there's a chance they could intersect. And if they don't intersect and they're not parallel, then they must be skew, because it's exactly what the definition of skew is. So, check one is parallel. To check parallel, we're going to compare the direction vectors. And you should know how to do this if you've been following along with the video so far. You should know how to find the direction vector of line 1. And you should know how to find the direction vector of line 2. So line 1, the direction vector, we're just going to take the components, the direction numbers, which are the numbers multiplying with the t, the coefficients of t. So -2, -3, and +1. Versus for L2's direction vector, we got 1, we got 2, and we got -1. And how do we mean compare? It's these are D1 and D2 scalar multiples. If you're having a really hard time seeing stuff like that, you could do the cross product, but I think that's a waste of your time. The real advice I would give is if you think these are scalar multiples, the easiest thing to check is to start checking the ratios of the direction numbers. So I have -2 over 1 versus -3 over -2. -3 over +2. No. They're not the same multiple. This would be 2, -2. This would be -1.5. So they're not scalar multiples. They're not scalar multiples. Therefore, D1, D2 are not scalar multiples. Not scalar multiples. Therefore, L1 and L2 are not parallel. Just to save space. So that means we failed to be parallel. If you did show the lines are parallel, you're done. You've done the question. So now we're going to check if they're intersecting. Again, from a blank slate. If they're intersecting, the first thing you want to do, very important, make sure you have or you use different parameters. There we go. The same parameter, like both t, like in here, would only check, would only check if they collide. And obviously that's a major concern if we're talking about airplanes, but more importantly, we want to see if the paths cross at any time, like if the flight paths overlap, right? They end up going through the same point in space, maybe at different times, like again, two cars with the intersection. So the first thing I'm going to do is I'm going to change, watch closely, watch line 2. I'm going to change line 2 in each of the 3 parameter spots to use a different letter. Now what we're going to do is we're going to start to solve a system of equation. Okay, then we're going to solve a system. So we have these 3 different equations for each line. So we're going to start by comparing the x's. For my x's, I have 1 minus 2t equals negative 3 plus s. I want to solve that for one variable. We're mostly going to be using substitution here. So that's 4 minus 2t equals s. For my y's, I'd have negative 1 minus 3t equals negative 2 plus 2s. If you're having trouble seeing where this is coming from, I'm literally just setting the two x equations equal to each other. Now the two y equations equal to each other. I'm going to substitute what I know the s to be. Negative 2 plus 2 times 4 minus 2t. Distribute and simplify. We're going to get negative 2 plus 8, which is 6, minus 4t. And I get t equals, almost messed that up, 7. That's a negative. If t equals 7, then plugging that into s, we'll get 4 minus 2 times 7, which is, of course, negative 10. And does that mean they intersect? Absolutely not. That does not show they intersect or not yet. Right now we have two variables. It means the x and the y line up. It means there is a time, like the 7 minutes into flight 1 and negative 10 minutes into flight 2, whatever that means, where they line up in the xy spot. But they could have different heights. They could have different z's. So then we're going to check our work using the z's. So z. For L1, we have z equals negative 2 plus t, which is 7, which is 5. So L1 at that time is at a height of 5, whereas L2, z is 3 minus s, so 3 minus negative 10, which is the number 13. So when they are at the same height, when they are at the same XY position, they're at vastly different heights, right? 5 miles up for L1, 13 miles up for L2. This means, so the lines don't intersect. And because we already checked parallel, it means the lines are skew. And that's my final answer. If we had gotten the same z coordinate, we would say the lines do intersect. If we had gotten the same z coordinate and we had s and t were the same exact number, we would say the planes in fact collide. I'll say that one more time. If we had the same z coordinates, all it means is the lines intersect. It does not mean they collide. If we got the same z coordinate and we had the same time parameters, if my s and my t matched, they do not in this case, but if s and t matched, it also shows they don't only intersect, they actually are going to collide. That's a good overview. We're going to do one more example. So let's strip away the window dressing here. Let's look at line 1, and this is why people might like the symmetric version. Here's a symmetric equation. Here's a symmetric display of information. Line 2, x minus 2 over 3, y minus 3 over 2, z minus 1. Okay, you might have to look at your notes from the last one, but the first thing we checked from the last video, first, check parallel. To check parallel, we need to find D1 and D2. Can you right now, looking at these symmetric lines, find the direction vectors? Where does the direction vector show up for a symmetric equation of a line? It shows up where the direction numbers show up. We have D1 equals -1, -2, 1. Where am I getting Z's direction vector from? Z over 1, everybody. Versus direction vector 2, 3, 2, also 1. Are they parallel? Not a chance. How do I know that so fast? The last two direction vectors are the same exact number. Sorry, the last two direction numbers are the same exact number. That means they should not be scaled at all if they were scalar multiples. So not parallel. Just to do a quick example of parallel, I'd be talking about D1 equals 1, 3, 4, and D2 equals 2, 6, 8. I don't want you to leave this lesson without seeing what it would look like if they were parallel. Do you see how those numbers are scalar multiples of each other? That's what we're talking about. Okay, so if you saw that situation, you'd be done. You would say the two lines are parallel. But we're not living in that world. I'm going to erase this now. So if we're not parallel, we're going to try to find the intersections. So I'm going to try to relay the X information, the Y information, the Z information. It might help you to be able to put these into parametric form. You should be able to put the line into parametric form. If you're having any trouble with that, we're going to show you the answer in a few seconds. I'll do L1 first. Here I go. I'd have X equals +1 minus T. So that +1 is coming from here. It's supposed to be X minus X naught. And the -1 goes here. One more shot. So this is for L1. Y equals, do you feel like you can do it? Try it. 3 minus 2t. Easy peasy. It's okay if it's hard for you. We're just getting used to things. And now maybe the hardest one, Z. What's Z doing here? 0 plus t. Okay? Can you right now try to give me the same parametric equations for L2? Use a different letter for the parameter. Use a different letter for the parameter. Use a different letter for the parameter. Here we go. Should be X equals 2 plus 3s. That's what I mean for use a different letter. Here I go highlighting again. The 3 is the coefficient of the parameter. The -2 became +2. At this point, you really should be able to get the other two. Here I go. 3, 2, 1. Y equals 3 plus 2s. And then for Z, it's just going to be 1 plus s. It's like all three of those parameters equal to s. I'm up here. And you're just solving for s. Or solving these two for s. Or solving these for s. Okay? That's how we're getting these. Please come to office hours if you're confused. What are we going to do now? We're going to start pairing these guys up. My x mess will be 1 minus t equals 2 plus 3s. You don't always have to start with x. If one of the other variables looks easier, do that one. This is manageable for me. I'm going to get -t equals 1 plus 3s, and then t equals -1 minus 3s. Can you right now pause the video and try to figure out what's going on with the other two variables? Use this and substitute and solve a system. Here I go. 3, 2, 1. For my y mess, I'm getting 3 minus 2t equals 3 plus 2s. And then I can substitute in the t's. Distribute. Be careful with your s's that they don't turn into 5s. 4s equals negative 2. S equals negative 1/2, which would mean that t equals negative 1 minus 3 times negative 1/2. Whew. What a trip. I think t also equals 1/2. Well, sorry, not also. T is 1/2, s is negative 1/2. And then what do we do with these two values? We're going to check them in the z coordinates. So I have t is 1/2 versus 1 plus negative 1/2. So it's 1/2 versus 1/2. Gasp, they match. So what does it mean? We found a t value and an s value where all three line up. We found a t value and an s value where the two lines have the same exact x, y, and z coordinates. What does that mean? L1 and L2 intersect. They do not collide. What would it look like if they collided? If they collided, it would mean the t value and the s value were the same exact number. So these intersect at, what's the coordinates here, folks? You could plug in the t value or the s value into each of your equations. Try that right now. I'm getting 1/2 to 1/2. And that's standard operating procedure. You plug in and you find the actual coordinate. Okay, that's a very long process. That's how it looks if they intersect. We talked about what it looks like if they're parallel. We talked about what it looks like when they are skew. It should be a standard thing. This is a pretty standard test question, if I do say so myself. Another example. Find where x minus 2, 3 equals y minus 3 over 2 equals z minus 1 is L2, right? That's L2 from the last slide. Crosses each coordinate plane. Okay. What does that mean? Well, each coordinate plane, remember, we have x equals 0, and that's the YZ plane. We have y equals 0, and that's the XZ plane. And we have z equals 0, that's the XY plane, your old home. Guess what you're going to do with this, right? Just guess. Well, if I know x equals 0, I guess I can plug it in. And I would get 0 minus 2 over 3 equals y minus 3 over 2. Which is, of course, negative 2/3 equals y minus 3 over 2. Negative 4/3 equals y minus 3. Y equals 5/3. And don't forget the z. Z minus 1 equals negative 2/3. Z equals 1/3. So where does it cross the YZ plane? 0. We already knew what that was going to be. 5/3, 1/3. That's how that process goes. Can you find these two intersections? Try it right now. 3, 2, 1. If y equals 0, we'd have x minus 2 over 3, 0 minus 3 over 2. X minus 2 should be negative 9 halves, and x would be negative 5 halves. Z minus 1 would equal 0 minus 3 over 2. And so z would be negative 1 half. So we have negative 5 halves, 0, negative 1 half. If you were really lost on these two, try that last one now. It should be really clear what we're going to do. And the last one I think is the easiest one. X minus 2 over 3 equals 0 minus 1. X minus 2 equals negative 3. X equals negative 1. Also, y minus 3 over 2 equals 0 minus 1. Y minus 3 equals negative 2. Y equals 1. So negative 1, 1, 0. Okay, so 3 intercepts for that line. It's kind of like it's going to cross each of these planes at a different point. One more idea here I want to go over. Find the angle between L1 equals the same ones we've just been dealing with. I'm just going to write them down again. Shouldn't be equals, I'm sorry. What they're equal to is t, or a parameter, right? And L2 was x minus 2 over 3, y minus 3 over 2, and z minus 1. These two lines, I'm not saying they look like this necessarily, but these two lines float in space and they intersect somewhere. Can we find that angle? Okay. This process is very simple. How do you find angle in 3D? What we've done before is find the angle between two vectors. So this process is just going to be find the angle between D1 and D2. Even if they intersect over here in space, remember all these vectors can translate back down to position vectors, so it's enough to always look at position vectors. How do you find the angle between two vectors? This is a quick review. If you can't answer this question right now, you're forgetting key important details. The way we define angle in 3D between two vectors, cosine theta equals, if that didn't ring a bell, we're going to do the dot product between the two direction vectors, and then we're going to divide by the product of their magnitudes. So what do I want to do? Just to be clear, what's D1? What's D2? Did you forget? Are you able to find it now if you did forget? Talk about negative 1, negative 2, 1, and 3, 2, 1. It's the denominators when they're in this form. It's the coefficient of the parameters in the other form. Okay. So this means the dot product here is negative 3 plus negative 4 plus 1. I think I'm talking about negative 6. The magnitude of D1 should be the root of 1 plus 4 plus 1, root 6. The magnitude of D2 is 9 plus 4 plus 1, or root 14. So cosine theta, I'm going to go way back up here so I don't run out of room. Cosine theta is negative 6 over root some number 84. And theta, the exact value would be the cosine inverse of this monstrosity. For those of you who are curious, is about 130.893 degrees, or 2.285 radians. And that's all there is to it. I know that seems a little abstract. I hope that was a nice review. This is a key skill. Thanks for watching this video. In the next video, we'll talk about planes and the equations of planes and the applications what you can do with lines versus planes and planes versus lines. It's going to be a lot of fun. Thanks for watching this one again. I'll see you in the next one. Bye for now.